All right, so I'm delighted to talk to you about deep generative models for fast calorimeter simulation, representing two groups of people doing these studies with the Atlas electromagnetic calorimeter and a future Kliq electromagnetic calorimeter. And two of the experts are sitting here in the audience. Dalila worked on the variational autoencoder for Atlas, and Sophia for the Kliq example that I will show. So outline, I start with these two EM calorimeters using a VAE and a GAN. I'll be very brief on the motivation, talk about the training data, the architecture optimization, model tuning, finally the validation and summary and outlook. So in a nutshell, what do? We are particle physicists. We are producing particles in our collisions. They're hitting one of our subdetectors called an electromagnetic calorimeter, producing an image, which is here a 2D projection, but is actually a three-dimensional image. This is a stochastic process. We are trying to use deep neural networks, in particular VAEs, GANs, to learn the underlying distribution, use the model, and then sample from this model to generate showers. And we actually train not on the data themselves, but we train on simulated data, which is produced by Geant, and which is inherently slow. And that's the reason why we want to speed this up by doing inference using these generative models. All of the material I will show is based on Keras with TensorFlow and using HDF5 formats. So the brief motivation. If you're not a particle physicist in the audience, you have learned by now that we do accelerate particles in big instruments. Then we collide those in the center of these big cathedral-sized detectors. What happens in these collisions is we produce many hundreds or even thousands of new particles. They will fly out through our detector, which is built like onions, different layers. In each layers, we do detection of these particles, and what we care about for this talk is the particles which fly into the calorimeter and leave these three-dimensional images in these calorimeters. Now, what do we do with them? We read out the information, and then we try to analyze what we observe. So we have to somehow interpret these photos. And it's very difficult from first principles to predict what we expect to see. So what we need is simulation to compare our data, in this case the black points, with, for example, a hypothesis to have only some background and to have here, for example, a peak, which resulted in 2012 in the Higgs discovery. So you see for this simulation that we will focus on from now on, we have a long chain starting with taking our underlying theory to predict what happens in these collisions, then what happens when these many particles fly through our detector, how do we read out, how do we reconstruct, interpret what we see, and finally analyze the data. Why do I show that? Because the bottleneck is really this part here, the simulation step. If you look at the CPU usage in 2017, for the worldwide grid, you see that 2/3 is used for this step of Monte Carlo simulation, and most of that is due to the particles going through the calorimeter. And why is this so CPU intensive? Because one particle flies in and it produces a whole shower, and each of these points you have to make a decision. Does it make an interaction? Does it continue to fly? And we do this at the microscopic level, making this a very CPU-intensive job. So we have actually found already a way to deal with this. Instead of using Geant to produce for us the showers, we have just use parameterizations. We use thousands of parameterizations to describe how the particles shower in the longitudinal direction, in the transverse direction. And this works actually quite well, but just not well enough to do so we can switch completely to this parameterized version. So that's why we think we can complement this current fast simulation based on parameterizations using the recent successes in deep learning, in particular VAEs and GANs. So what do we use as a training sample? We have 100K of these J-on-4 showers, and for the moment we focus on photons, which deposit all the energy in what is called the electromagnetic calorimeter. We have discrete energies, logarithmically spaced between 1 and 260 GeV. We focus on a very narrow range in eta, and then we pick a window around the cell where the particle hit our calorimeter, such that we catch, on average, 99% of the shower energy. Now, this is only one layer of the EM calorimeter, but we have more. We have a total of 4 layers. Now, the difficult feature is that the granularity changes of the individual layers. Whenever we need granularity to improve our particle identification and reconstruction, we make it more granular, as for example in the front layer, which continues all the way. And then in certain other layers, it doesn't matter so much, and we have a coarser granularity. So this makes it a bit more difficult to handle this. It's not a truly uniform 3-dimensional image, but it's rather layers with different granularities. In addition, we have one more feature in our data, that is, and as you move through the detector and deposit your photons in different parts of your calorimeter, the relative alignment of this middle layer, the front layer, or the back layer changes. So this introduces an additional complication. Right. So we use 2 different deep models. The first is a variational autoencoder, and here I show you the architecture. 4 hidden layers. You first go down in the number of units per layer, and then you go up in the decoder. You have here in the middle the latent space you sample from, which is of 10 dimensions. This is the total number of cells, these 4 layers, and you condition it with the particle energy of your truth photon. Now, in addition, you have to decide what you want to optimize on, the loss function. So you have the standard reconstruction loss based on the mean squared error. You have, as a regularizer, the KL divergence. And then, in addition, we add 2 terms to the loss function. The first one here to constrain the total energy deposited in the calorimeter, and the second one is to constrain the relative energy fraction in the 4 individual layers. They are all associated with individual weights that we can now tune and optimize on. So we do this. We do a full hyperparameter grid search. In addition to the weights, we also have we vary the latent space dimension, the number of hidden layers in the encoder and the decoder, the number of units per layer, activation function, etc., etc. And I highlight here what turns out to be the most relevant for the optimization, which is the weights in the loss function and the latent space dimension. And then what do we use to tell has our model improved or not? At the moment, what we decided on is to take a KS distance between the synthesized showers and the original J-on-4 showers, and look at the total energy deposited to decide is our model improved or not. A word on the convergence: 100 epochs within 2 minutes on some reference CPU here. So this is one example of the hyperparameter optimization. On the left, we vary, for example, the weight of the KL term, and you see the black dots are always the true data we train on, and then here, as you vary the weight, blue and red gives different level of agreement for this distribution. Here on the left, the energy. On the right, for example, how the energy is distributed in the eta direction. And here we vary the learning rate. You see how it changes the distribution. Now we have a second architecture. So a second approach is to use a GAN. And this is an overview over the architecture here. A generator producing a generated shower, sampling from a random distribution. Again, you give it as a conditioning the particle energy. In addition, we also have here the different alignments of the different layers as a conditioning. And then the job of the discriminator is to compare how well can we tell the generated shower from the Geon4 training sample. You define a loss function based on this, using also the Wasserstein distance as to define a distance. And at the end, we do again a hyperparameter grid search, where you see here the parameters we vary. And the most important ones in this case are the activation function and how we condition the modeling. And this here is for reference the convergence, and you see we use 2 minutes for the VAE, and here it takes quite a bit longer, 7 hours for the architectures we chose, and using only 5% of the training statistics for the VAE, we use the full statistics available. Now, how do you do the validation for this? How do you convince yourself that your generated images really look good enough? And what we can do is we can basically say if the observables that we use to do physics are well enough reproduced, then we are happy. You can think of this, so I will flash now a couple of examples as just projections of our high-dimensional images into one-dimensional distributions or moments of the distribution. So I'll start by showing you the total energy deposited in the individual calorimeter layers. This is, for example, the barrel 1, where the largest amount of energy is deposited. This is for photons of a certain energy. And what you see already is some level of mismodeling on the tails, and we believe this is due to the fact that the correlations between energy deposits in the different layers is not well modeled at the moment, so this needs some further tuning. And in particular for showers which start very late, sometimes the photon goes deep into the calorimeter and only starts then showering, this is exactly this part here, are not well reproduced. Now this also then shows up in the total energy. Now you add up all the 4 layers, and you see that this mismodeling leads to longer tails in our synthesized showers as compared to the training data. And at the moment, in blue, in the GAN seems to do a slightly better job for modeling these correlations. Whereas the energy, the reconstructed energy, seems to be quite well modeled. So this is the average energy as a function of the truth energy. So here going from 1 GeV to 260. Comparing the black point, the data with the 2 models, VAE and GAN, seems quite good. The longitudinal shower center, this means how deep is most of the energy deposited in the calorimeter, is more difficult to get right for low energies and gets better modeled if we increase the energy of the photons. And finally, I flashed 2 more, which is how the energy is distributed in delta eta around the center. This is for the 1 layer which has the very fine segmentation in eta, reasonably well modeled, and then in phi as well, where the binning is much coarser. Okay, so this is for the Atlas studies. Now I'm moving on, and I tell you basically the same story for a future electromagnetic calorimeter based on the Kliq linear collider detector studies. So here, giving you some information on the calorimeter. The feature is it has a much finer segmentation, and it has a uniform segmentation. It's 5 millimeters everywhere. 1 million single particles are used as a training set, not only photons, but also electrons and neutral pions here. And the energy spectrum similar between 10 and 500 GeV, but in this case flat, as compared to for Atlas, we used individual energy points. Incident orthogonal to the detector surface, plus minus 10% random incident angle. And here you see how a shower is developed in 3D. As I mentioned already, what is the most important differences between the Atlas calorimeter and the Kliq one? First of all, this is uniform here. Same number of cells in all directions, where for Atlas it was quite non-uniform. And you have also the total number of cells is quite different. So it's a much larger number of cells for Kliq. As a result, you get these very sparse images, right, where you have most of the energy deposited just in a few cells. This is the XY, and here you see also the longitudinal direction. Now the architecture is the following. It's a GAN, where again discriminator and generator use a similar architecture. Use 3D convolutions, and you keep the XY symmetry of your showers. The shower, if it hits perpendicular, you get basically the same kind of distribution in X and Y. Several tips and tricks were used. RMS prop is used as an optimizer and batch training. So in addition here, to improve the convergence, conditioning is used not only on the energy, but also on the particle type, because more than one particle is used, and on the incidence angle. And then in addition, an auxiliary regression task is assigned to this model. And here the idea is to reconstruct, the task is to reconstruct the primary particle energy, as well as the deposited energy in the calorimeter and the incidence angle. And this helps to in the convergence. Here, just some validation plots that show you that indeed the loss real over fake is around 50%, as you would expect, and also the generator loss decreases, the discriminator loss increases as expected asymptotically to the right value. Coming back to validation optimization, again for the validation, you look at your physics plots, high-level quantities, detailed calorimeter responses, particle properties, and when you define what is good enough for you, and this is your validation. And for the optimization, a sort of hyperparameter grid scan is performed, varying the architecture, definition of the loss, pre-processing, and here explicitly you don't try to constrain any physics variable, but you only play with the GAN loss. So overall, very good agreement at the few percent level, and I'm just going to show a couple of examples in the next slides. So one is similar to what you saw for Atlas. What is important is how is the energy distributed along the particle direction. So here it enters and it flies through, and most of the energy is distributed in the middle, and this here goes to the end of your 25 cell window. It's a bit harder to do it for lower energy. It gets easier if you have a higher energy electron in this case. You can do the same with pions. Look again at the longitudinal one, but now also at the transverse directions. And in all cases, you see decent agreement for these shower shapes. Then here is the fractional energy reconstructed over the truth one as a function of the truth energy for electrons and for the neutral pions. Again, some small discrepancy at low energies again. And here it seems like there is an overall offset of the energy for the neutral pions. Then you can also check how is the regression task performing, right? You check your reconstructed energy as compared to the truth energy, and here you see you do a very good job. Basically, within 5%, you get back the truth energy. Finally, I will show one variation where now, instead of the perpendicular incidence, you go to a region of your calorimeter where you expect the incidence angle to be different from perpendicular. For example, you go to plus minus 30 degrees. So now you see already you don't have any more necessarily a symmetry between x and y, the transverse direction. So this requires some adjustments to your convolutional parameters. Also, you have to make your overall window larger to capture the full shower. And this requires some further architecture changes. And you see this is really work in progress, hot off the press at the moment. This still is still not giving you the precision you want to reproduce the training shower. So here you see some discrepancies, but this is, as I said, still a work in progress. Now the last slide before I summarize is to tie this back with another talk you saw earlier in the session 04, which shows you that indeed you get for the inference the speed up that is much above what you need. And here also some reference to the work being done on improving the speed up for the training. And as you increase the number of workers, that shows indeed that you can speed up the training using parallel training and MPI. So to summarize, fast shower simulation is essential for Atlas and Kliq physics program, and for that matter, it's crucial for the whole high energy physics, particle physics experiments. I showed you here a proof of concept that these generative deep learning models seem to do a good job to simulate particle showers. The agreement is promising, but still not sufficient for the accuracy required to use this for large-scale production. And maybe as an outlook into the far future, maybe we can use this also to generalize and for different architectures and different detectors to use these kind of techniques for simulation. Thanks a lot.
Thank you. Are there questions? Yes?
Hello, thanks for the talk. I'm not a particle physicist, so I apologize if the question is based on a misunderstanding. But it seems to me that the new physics results you aim to get from the data, that these are mostly based on rare events. Mm-hmm. Are your loss functions adapted to reflect this, that you especially focus on minimizing the loss that would lead to new insights?
You're asking about this context here, the calorimeter simulation, right?
Yes.
Yeah. Okay. So this would, if you want to apply that also for a search for a new phenomena, here the assumption is that these new particles would decay back to the particles we know, such as electrons, photons, and pions. If they would decay into something else, or they would leave a signature which is different from this, then we would have to make a hypothesis, right? And say, okay, the hypothesis decays to something else, and then we would have to adjust the training to be able to model that properly.
If I may also keep commenting on this, I think it also, I mean, we are still really starting with all of this work, right? So we need to see where we get in terms of performance to actually decide what will be the use cases that we'll be able to cover. So we know that correct simulation of rare events is a particularly difficult task. We'll have to see. Are there more questions?
Hello, I'm also not a particle physicist, just so you know. But I'm wondering, so basically, in reality, the variable that you're interested is the energy levels which are discrete, right?
No, these are not discrete. This is the energy, for example, of the particle. Okay. And certain properties, which like how's the distributions I showed, how's the energy distributed in the particle direction, in the flight direction, and transfers to it. And these distributions allow us to infer, was it an electron, was it a photon, was it a pion? So this is the problem we have. Many particles fly out in the data, but we don't know which particle is which. So only from these detailed distributions we can tell with a high enough likelihood which of the particles it was.
So generally you use floats in order to do all this business, right? Floating point numbers in the end, in the whole network.
Usually it's floating point numbers, yes.
Okay.
Yeah, we are right now running with single precision, but we would like to try and test to go even lower, actually. We might not need it.
If I can offer some intuition, basically this wavenet that the first speaker was presenting, one very important trick that they did was that they used psychoacoustic coding. So basically they took, in order to produce so nice results, they actually took and discretized the floating point numbers in such a way that they are more refined in regions that they know are more important for the human listening. So maybe something like that is also applicable in physics, I don't know.
I mean, it sounds like, yeah, you dynamically adjust whenever you need more precision, you use more precision, and you don't, yeah.
Okay, which I ask? Okay, since I have the microphone. I mean, it seems like, you know, on the Atlas studies, it didn't really achieve the precision that you get in the Kliq analysis, maybe. Is that fair? I don't know.
I mean, these are really very preliminary results.
Sure,
so
sure.
we just tried first.
You've been trying for a while, and Michaela.
Well, we're trying.
Yes.
So we are hopeful this will improve.
Right.
It's just a sign of life. Yes, we're doing this in Atlas.
Right. I mean, I guess my point was, I mean, so we have a cosmology example which we use where we got, you know, like extremely precise reconstructions, and then we have other examples like this RPV-SUSY type thing where it's really not precise at all. And I was just wondering whether there's some general understanding that either you have got or we can get about where it works really well and where it doesn't work. Because, you know, that could help us guide what examples we put or help us transform the data in a way that would make it work better for all cases. I don't know if you have any answers.
I would love to have an answer to this question, yes. So at the moment, I don't think we can say for sure.
Because at the moment it seems we're just throwing the data in and we're going in and we plot distribution and it looks terrible or it looks amazing.
Right. So at the moment we don't know, is it due to the data? Is the problem in the data, or is the problem still in the approach, right? Can we just find a better model and then
To me, it seems like it's getting some properties of data, like some of the things in the cosmology case are essentially just Gaussian fields. They're like Gaussian fields or what have you, or there's some, you know, 3-point correlation or something. There's some function of the data that you know, maybe you could reason in some way that it can learn because they're composable in some ways from layers. And then some of the other distributions, it's more difficult to see how that physics distribution relates to a statistic on the image. See, so that's just. But on the other hand, celebrity faces, how do they? No.
If I might just comment, we have like really imbalanced data sets where we have really low energetic showers and very, very few statistics of high energetic showers. So the model does learn how to reproduce the low energetic and not the high energetic. So it's really a problem how to reproduce the tails of the distributions. So it may be related to that, but let's see. Yes.
Other questions or comments? If not, we can thank yes again. And we close the workshop.